to a couple of minutes.
Right.
Okay, first we of your cell phone. Well, your presence or absence here by this week, those are not important. The absence and presence for next week will be counted, right? What we'll talk about a little more about the method of steady state. And we basically talked about the concept of steady state methods. And we built some simple problem, a simple one. And now let's start a little bit complex. As I already thought, the problem is very, complex because you need to consider all, environmental factors related for the environmental effects. It will be from the microbiology side. It will be from the chemical side. It will be from the geological side. Well, anyway, as I already thought, understanding the problem is very, very important. And then you simplify, your simplification is very, very important. One of the most easiest way to simplify your problem is to set up system boundary. What is the initial and what is the final called equilibrium system boundary? And then what is the boundary conditions? And one thing you should do is to draw the schematic diagram of the system. Right? Let's start the problem. A non-volatile, chemically stable, and highly water-soluble solvents. Let's say sodium chloride salt. Is sodium chloride able to be contaminants? Can it kill you? Yes, that's right. That's right. Well, sodium chloride, in the study in the day, you run and run in marathons. If you cannot consume appropriate amount of the salt, well, you can be easily dehydrated. Okay. So that is the reason why you guys want to drink Gatorade. Why? Is Gatorade better than water? Why is it better than the water? Any thoughts?
Because it contains many ions.
What? Well, you think ion can help something, right? So what is the main role of the ions?
To make it absorb better to human body.
And
Provide essential ions to the body.
yeah, actually he is from the Gatorade. So I think that is very nice hypothesis. But the why Gatorade is better than the water is it can stay water more time in your body. If you drink water, the water can be discharged from your body maybe 5 or 6 hours. If you just put some sodium chloride, anions or cations, it can stay longer time. So that is the reason why you want to drink more, sodium chloride water, right? Or Gatorade water. So, well, basically, based on the chemistry, biochemistry, well, drinking Gatorade and drinking the same amount of, the same concentration of, we call it electrolyte, the cation and anion, the same concentration, well, you can not be easily dehydrated. So you can drink the salt water. The problem is nobody wants to drink salt water equivalent to the concentration of Gatorade because it is salty. Right? Well, anyway, as I already taught, the concentration can kill you, the high concentration I mean. So the sodium chloride can be contaminants in being dumped into a lake at a rate of 0.16 tons per day. Well, you guys cannot imagine if somebody just sit in the lake side and then dump sodium chloride every day. Oh, who want to dump this salt into the water? Although you can sell it to the people, right? So what kind of environmental problem can you have? What kind of environmental problem you can have by discharging or by contaminating groundwater by the salt? Well, can you find such kind of salt contamination? Think about the Jeju Island. Have you ever been there? Yeah, well, if you have a chance, please visit, and you can find some very wonderful spots. Well, anyway, near the seashore, well, actually, Jeju has very good groundwater resource. So they sell it. The name Samdasu. Well, you usually buy it, as a drinking water. The problem is near the seashore. If you just drilling the seashore ground, well, the seawater actually can enter into the ground, right? So the seawater can contaminate groundwater. The problem is you cannot drink the seawater. Have you ever drink the seawater? Yeah, she has actually had the experience. Don't do that. Well, anyway, it is not good, drinkable water. Anyway, at that, situation, at that event, we call it salt water contamination, right? Well, anyway, just assume somebody want to dump salt, and solid salt, into the rake. So the rake has a volume of 4 times 27 cubic meter, and the average water flow rate through the rake is 8 times 10 to 4 cubic meter per day. Well, anyway, you know evaporation. Evaporation is very, very important, right? From the rake surface, and assume proton is uniformly mixed. This is also, silly assumption, right? But let's assume the salt uniformly mixed. Is there any bad guy who just dumped sodium salt into the rake and then uniformly mixed that salt to contaminate the groundwater, rake water? Well, but this is very silly though, just for the easy understanding of the problem. Let's assume this. If so, what is the steady state concentration of this proton in the rake? Let's calculate. Well, actually, this problem we just copy and paste for writing Ronald high school. Well, this is my idea. But anyway, Ron just want to put it in his textbook. Well, anyway, at first time, we need to set up the system boundary, right? So some body want to put 0.16 ton per day salt into the rake. Maybe he is a millionaire without any thoughts. And then the volume of the rake is 4 times 10 to 7 cubic meter, and the water actually goes out 8 times 10 to 4 cubic meter per day. This is very, very interesting. Is there any water comes in? No. Just water always stay 4 times 10 to 7 cubic meter, and then it just goes out 8 times 10 to 4. What kind of cases can you assume for this environment? Just like there always same amount of the water there, and some amount of the water just goes out. So where is the water source?
Groundwater?
Yeah, you can assume that. But the problem is there is not much, or even I don't think there is such kind of groundwater source to provide this amount of the water. Mostly from the sky. So think about the related equation. Well, actually, we want to know the concentration of the proton in the lake. So the concentration is stock divided by volume. This is very simple, right? And the stock equals flow rate times hydraulic retention time. So we can get concentration F flow times retention time divided by volume. This is very easy, right? All right, here we know the flow and volume of the lake, but we need to calculate the residence time of the pollutant in the lake. Well, this is very easy one, because if you just put the salt in the water, salt can be easily dissolved, right? So the retention time of salt contaminant equals the retention time of water. Can you get that? But what if we just want to contaminate? Well, this is just an assumption, right? Contaminate the groundwater or lake water with wasted oil. In that case, the residence time of water equals the residence time of wasted oil. Yeah, you should just I would take it as a no. Well, this is very difficult to estimate the residence time. But think about this. The problem itself, well, we really need to solve the problem because this is environmental problem, right? But at first time, if we want to solve this one, understand this problem, we need to simplify all the conditions. Even we simplify, the bad guy just want to dump, very valuable, precious, expensive salt into the water. That is totally right. And also, the bad guy want to mix it to make, constant concentration. But in fact, for real-world environmental problem, the concentration, uniform concentration, it cannot be made. The concentration itself should be different with respect to depth and with respect to distance. Is it? And also, the retention time of salt can be different. Well, actually, we don't want to, dump salt into the lake, actually, right? Wasted oil, it can be, floating around everywhere. So any spots of the wasted oil, residence time should be different. But as an environmental engineer and environmental scientist, you guys need to solve the problem, the concentration. How can you solve it? At first time, you start with very simple assumption, simplification, and then you consider each item. And you can finally solve that problem with exact, estimation. Right? Right. Well, this is a little bit silly. The residence time of the water equals residence time of the contaminants. So the residence time can be calculated, stock divided by flow rate, and we just put the values from the given condition, and you can have 500 days. Wow, 500 days, right? It is around the almost 2 years. And then the concentration can be, can be obtained by this calculation, flow times retention time divided by volume. Well, you can get 2.0 ppm. Well, here you actually need to assume one more, the density of water. Actually 1 gram per cubic centimeter. Well, if you really want to know the concentration, the exact concentration, well, you really need to consider the different density of the water with respect to temperature and with respect to any related environmental factors, right? So this is the reason why we want to do some simple calculation. Let's say, you can say, Professor, well, actually, we don't have to estimate this. Well, just to measure the concentration. Take the sample and put it into ion chromatography, we can get the concentration. Well, that's right. That's right. But what if you have some kind of, problem, situation, you cannot get it from the real analysis? For example, sending people to the moon. Right. Well, if you are using the estimation, you can actually design the rockets, the fuels, without, killing the people. But under the analysis phase, well, you can conduct the experiment. But people, the astronauts, can get killed. So estimation is very, very important, right? And the estimation starts with very simple, simplification with assumptions, right? Yeah.
We take some assumption very far away from the reality. For example, you were saying that it's mixed, but in reality it will be like if it's strong, then it will go deep in the water and stay.
Yeah.
I think it's more like this. So if our assumptions are very far away from the reality, how can we approach our result, false result, to understand the result?
Yeah, well, it is a very good question. Well, this is just a made-up question. Just understand the steady state equations and how to calculate it, how to estimate it. But the real world environmental problem is totally different. Totally different. So, well, actually, if you just visit the site, well, you know the situation very well. For example, let's say the contamination. Well, 3 or 4 years ago, the oil tanker actually wrecked up and spilled maybe 1,000 tons of the crude oil into South Korea, and all the Korean people freaked out actually, and then they just visit there and they help to clean the rocks or sand using crudes actually, which turned out to be very useful and effective, I think. Well, when we just started to solve some kind of environmental problem, well, we cannot actually understand the real source of the problem. Well, in that case, we really need to have good assumption. And then we run the estimation, and we can have some kind of estimation results, and then compare the results with the real reality. And then we just find out, well, this our first assumption is wrong, and then we just go to the another one, and then run again. In that case, we can use both simulation, computer simulation, and also analysis. Right. Okay. Anyway, there are many different approaches to solve the environmental problem. But the important thing is we need to actually go here. All right, and then the author of this book actually added some more real environmental conditions here. What if all this pollutant came into the lake with a lot of water? Well, actually, there is nobody who wants to dump the salt into the lake. So the author, including me, think well, in this case, let's do some more natural case salt water. Well, we can actually imagine the seawater getting into the lake, actually, near the seashore. For example, Gyeongpo Lake, which is located near the seashore. Well, maybe, some environmental episode, the seawater came into the lake. So the question is, what if all this pollutant came into the lake with a lot of water, let's say 2 times 10 per cubic meter per day? In this case, what would the concentration be? Well, actually, this is the reason why you guys want to do some engineering, not the science. Think about that. How much is the 10 to 4 cubic meter per day? It is around the 10,000 tons per day. Have you ever think about the size of 10,000 tons per day? You actually need to design wastewater treatment plant and water treatment plant. to provide clean water. You know, well, chemical engineers and I'm very sorry to chemists here, but I really need to say something about this. Chemists actually can calculate and can do something. But the important thing is, if you cannot do engineering, how can you deal with 10 to 4 times cubic meter per day? So this is the reason why you need to do some civil side engineering with environmental engineering. So how to deal with this, size of the water? Think about that. If you just dig the ground and take out all the wastewater pipe, system, and what happened there? The wastewater just discharge it, and you can find the wastewater everywhere, right? So what you should do as an environmental engineer who is, majoring in civil engineering department is designing the plant, wastewater treatment plant. Have you ever visited there? No? I think this is a good time to have site visit, actually. Well, anyway, so we are dealing with this size of the water and the concentration. Well, the calculation itself is very easy. The total flow rate of water is, because we have 2 times more, so 2 plus 8 times 10 to 4 is 10, right? So 10 times 10 to 4 cubic meter per day is the total. And then we can also calculate the residence time of the salt, which is 400 days. Think about that. If you add more water into the lake, and the residence time of the salt can be shortened, right? Then you also do the same calculation for obtaining concentration. So just adding the new residence time 400 days, and then you can have 1.6 ppm. Because if you provided more water into the lake, and the concentration of the protein, salt, can be decreased. Right? All right, and then you simply calculate and estimate the concentration by dilution. Previous case, you used 8 times 10 to 4 cubic meter. Now, you're using 10, right? So just divided by this portion, you can have 1.6 ppm. This is very simple. Right. The next case is, what if 1/3 of this water evaporated? This is much more like environmental problem. The evaporation is very, very important, right? So would this change the concentration of the protein in the lake? How?
Less water means if it stays there, then the concentration will go up.
Yes, that's right. The concentration actually going up. Well, because this is very simple, estimation. Because we are using 1/3, so just divide it by 2/3. Well, you can have simple calculation actually. Here, so divided by 2/3 here, you can have 600 days of residence time, and you can have higher concentration of salt, right? This is for granted actually. So actually, we have dealt with some silly, simple environmental problem for understanding the steady state. Well, as you guys always said, the concentration, the significant environmental factors actually does not change with respect to time in steady state case. This is very important. Let's do more complex environmental problem. Adding some more flows. Well, just the flow comes in and flow comes out. That was what we are doing for solving these environmental problems, right? Okay. Just assume several processes by which something can be lost from a compartment. Each process has its own flow, which is given by stack times the rate constant. Well, think about this. The previous one is a stack and just goes in F1 and just goes out, right? But in this case, we can think about some multiple ways. And think about the So if we just set up the mass balance simply, a compartment with three flows, F1, F2, F3, just going in into the rake, and three flows going out, numbered F1, F4, 5, 6. So we can actually do some steady-state mass balance here using flow. So M1 K1 plus M2 K2 M3 K3 equals M4 K4 to M6 K6. Well, this is very simple equation here. And then, well, just to do some simplification of this case, let's assume we have one compartment with three processes. Just think about this head. All right. And then we can put it all of the addition, sum of the this flow as a total, head total. So it could be explained by M total times K total. So it could be M1 K1 plus M2 K2 plus M3 K3, right? Then, if we assume the M total equals all the stock going in, we can simplify K total would be K1 plus K2 plus K3. This is rate constant, and it can be converted to the residence time. So 1 over total residence time equals each this reciprocal of residence time of the summation of those. Well, related environmental problems will be popped up the next time. And then I really want to introduce very important concept, flux. What is the flow? Snowman over there.
Yeah. Flow?
Yeah, what is the flow? We are dealing with the flow so far, right? So what is flow?
Flow is just all of amount of something flow. All of something flowing water.
What is flow rate, if so?
Flow rate is that all amount divided by time.
Right. What is the flux? Have you heard about flux?
Yes.
Are you a civil engineering student?
Yes.
Sophomore? You don't know you are sophomore.
Yeah, second year.
I think I need to speak to him in French. By the way, what is the sophomore in French? Yes.
In 5 years, because we have 2 years general engineering and 3 years for.
So there is no such kind of specific words. Just the first or second like that.
Actually, it depends on the school where we are. We have each school has its proper slang to describe.
Okay. Well, actually, I cannot speak in French. Okay. So you're a sophomore.
Yes.
And are you having fluid mechanics?
Yes.
So you know the flux, right?
Yes.
What is the flux?
Flux is density of, maybe means density of flows that.
Density of flow. Wow, that is a little bit
Yeah, so
sensational.
sensational. Wow. So flux means flow divided by unit area.
Well, actually, flux here. Yes, sir. Okay. Well, flux and flow are totally different. But most of the engineers, especially chemical engineers and mechanical engineers, even civil engineers are using flux for their numerical simulation. So this is the reason why we want to know flux. And you guys, or even the experts like me, usually cannot distinguish it. So I always ask them, is this flow? Is this flux? So totally different. So please remember this. The flow of something from a compartment per unit area of the surface through which the stuff is flowing is called the flux. Wow. Super, right? Well, I really don't know. Ron actually want to use, stuff, he really like the stuff. What kind of stuff? Stuff like this, like that. Anyway, flux is a rate of equals amount stuff divided by times divided by area. So amount can be, stuff can be explained by the concentration time volume, right? And so time area, and also the volume is area height, right? And the area can be cancelled out each other, and it could be concentration time, height divided by time. So height time, well actually this is velocity, right? What's the difference between speed and velocity? Any idea?
Velocity is like vector.
Right. Wow. You guys really, know a lot actually. Because Ron Heinz is very famous, chemist, physical, analytical chemist. He is the editor of the analytical chemistry. Now he's around 7 years old, very old guy, very big guy actually. Anyway, but he usually don't care about the mathematical thing because he believes mathematical and physics are useless. I believe so too. So, well, think about this. Height divided by time. This is length divided by time, velocity, right? But we are using height, not the distance or length. Sometimes we call it deposition velocity. Think about this. As I already taught, the PVDE, fire retardant, it can be easily transported from one area to the other. So even the curious polar bear family can be contaminated by such contaminants. Even, as I already thought, the model milk, you can find it, very small amount. Well, anyway, it's just the particle of PBDE can be transported, and there is no wind. It's just falling down. So we want to measure the speed, the velocity of the particle falling down. So we call it deposition velocity. This is very, very important for the atmospheric chemist or atmospheric environmental chemist. Well, anyway, so the flux can be defined as deposition velocity times the atmospheric concentration. Right? Units, well, velocity, length centimeter divided by time second, and then atmospheric concentration, the final retardant PBDE picogram divided by cubic centimeter. So it could be picogram centimeter to minus 2 times reciprocal of the second. All right. So as I already talked, as the snowman over there talked, the flow is flux times area. The flow is flux times area, and flux is flow divided by area. This is very, very important. Well, if you will major in chemical engineering, so you will do some chemical mathematical computer simulation. Remember me. Flux is very, very important now. All right. Okay, let's do some example problem. In a remote area of Nepal, the concentration of aluminum in outdoor air at ground level average is 94 nanograms per cubic meter. What is the ground level? How can you call it? How can you categorize the atmosphere with height? Well, there is atmosphere, and then you can say louder.
In French, it's troposphère.
Well, I'm very sorry. I don't know.
No, you mean the layer in the atmosphere?
Yeah, the question is troposphere is right. Troposphere. The ground level, we call it a troposphere. The level you are breathing, troposphere. Yeah, inhale, troposphere, and there is atmosphere. Other strata. And the aluminum concentration is around the 94 nanograms per cubic meter. Wow, this is very, very, very low concentration, right? But anyway, here, well, before starting this question, do you know the guy's name, the famous Korean marathoner, Woojin Lee? Well, actually, he is 3 or 4 years younger than me. But if you just compare me and the marathoner, who is actually older? Who looks older? You don't have to, practice speaking. You guys understand what? Is it difficult for you to answer with questions? Yeah. Yeah, looks older, right? Not older actually. So why he is so looks older? What make him just like the 50 years or middle-aged man? What make him older? The female student here, you guys are very, anxious. I mean, care about the skin, right? I let you know the KAIST, female student really have interest in their, skin, but this is if you know chemistry, you can have good diet, you can have good skin, actually. So what kind of thing, chemical compound can make Mr. Lee older?
Oxygen.
We are breathing oxygen, so we are getting older and older, right? With respect to time, right? But we don't believe the oxygen O2 itself, make harm to us, right? Is there any more, we can say hazardous, or especially to the female student, could be hazardous for their skin health. What is it? What can it be? Have you heard about the activated oxygen or hydroxyl radical and nitrate and ozone? Let's say, O2 is very, very good, right? If you just increase the O2, well, you don't think O2 can kill you. If you just visited Japan, especially at the Japanese airport, you can find the oxygen shop. It is just like the masseuse parlor at the airport in Thailand. If you just get in there and some nice looking girl, give you some kind of mask on your nose, and just increase the concentration of oxygen, and you can breathe it. And then they charge you $50 for 30 minutes. So oxygen is not the containment, right? But the problem is, if we add one more, you can get ozone. Is ozone good or bad? Like that. Have you heard about the atmospheric? In that sense, can you say ozone is bad?
No.
Right. So in the troposphere, ozone is very bad to US, right? You can smell ozone if you just drop by or passing by the coffee corner over there. Well, actually, the high voltage actually can make ozone very easily. Why ozone is so harm to us? Well, there is another. What is OH dot?
Radical.
Yes. Chemist over there? How do you put it?
Radical?
What radical? OH.
Hydroxyl.
Yeah, hydroxyl. Hydroxyl radical, right? Hydroxyl radical. Also, and even nitrate. Well, these are, if we can measure very small amount of these radicals, actually, in the air, this is very rapid. So it can actually make you, older. These are all the oxidants. So if you are exposed to the oxygenated environment, I mean, not just the environment like this, highly oxygenated environment. Let's say the coffee corner over there. If you just stay there, now you are earning your age. No, I really mean that. This is very, very important. Even this ozone and hydroxyl radical if the concentration increased by 10 times, in the area like this, well, that can cause you asthma. This is very, very, significant fact actually. So this is the reason why we want to measure the concentration of each chemicals in the air. Right? What about this is average aluminum concentration of Nepal. Who cares? Do you care about the aluminum concentration of Nepal? But the important thing is, if the concentration of this one increased by 10 times, well, this could be the very, worst environmental problem in the world, right? So anyway, the concentration of the pulp is 94 nanogram per cubic meter. Well, I will talk about the looking old story next time. Please focus on this problem at this moment. It is much higher inside in the room. The sulfur dwellings because of the wood and yapdown burning. Well, those materials include aluminum, so the concentration can be increased in their house. At the same side, the aluminum concentration in top 1 centimeter of fresh snow averages 0.12 microgram per gram. This is ppm. While in the top 1 centimeter of 3-day-old snow, it averages 0.2 microgram per gram. What is the average deposition velocity of the aluminum falling to the ground when it is not snowy? This is quite a difficult and complex environmental problem, right? Well, although this is not the when we talk about the environmental, we kind of have tendency to relate the pollution thing, but just focus on the environmental. If you just focus on the environmental, you can relate not the contamination. You can relate the natural phenomenon. This is the natural phenomenon, all right? So how do you estimate this? Because the snowman over there already talked about what is the flux. You guys can use flux. And then using the flux, well, as we already have taught, flux can be calculated by deposition velocity times
concentration.
Yeah. Well, anyway, we will deal with this example question next time. And one more thing, I just want to give you as an interesting one. Well, this is radon question. Have you heard about the radon? In Korean, we call it yeah, right. Well, when I was, elementary school boy, there is very many, general, ordinary bathroom. Not bathroom, washing, facility. There are many, facilities in Korea, and sometimes I can, see. Yeah, there is just like this type of the advertisement, board there, and then they just put it our facility and our hot water include radon. Yeah, you guys may be very just like this, but at that time they just put it at the radon. So please come visit and have some kind of good effect of the radon. Think about that. Why radon is so good? Well, anyway, we will talk it later with some interesting and silly stuff.
Well, anyway, is there any question or comments on it? No? Thank you.
감사합니다.